Well, for the last 1.5 hours, I was sitting over there in the audience, and I was listening to my amazing colleagues. And to be honest, I was starting feeling more and more intimidated. And the question that I kept asking myself is, what am I doing here? I'm just a theoretical physicist. And yes, I know the stereotype, and I appreciate it. So rather than trying to justify why I'm on stage, let me formulate a goal. What is it that I would like you to take out of this 10-minute course on quantum physics? As you might have heard, this tiny prize, this big thing, sometimes called Nobel Award, Nobel Prize, was awarded for groundbreaking experiments in quantum physics. What was that really about? Well, obviously, I won't be able to tell you everything about quantum physics that you would like to know. But maybe, and this is really the minimal goal that I'm hoping to achieve, I will be able to inspire you to reflect a little bit more about reality. And what I mean by that is, what is real and how do we know where we are? But let's start very, very simply. What do you see? What is this? Well, it's just a rectangle, right? All right, cool. What do you see now? Well, what if I told you that both times you were right, while at the same time you're also totally wrong? What do you see now? So what you appreciate here is that depending on the perspective, depending on how you measure, depending on how you look at things, you might get very, very different statements that fully describe your reality, your objective reality. However, you might also be losing out on the full absolute truth of the universe because you don't have access to complete information. Why this is really important is because most of the physics that we describe, most of what we see around us, is built on experience. Let me ask another question. And Carl, don't worry, I'm not going to actually do it, but let me ask you, what would happen if I threw this remote towards you? Well, pretty much everyone in the room would make a prediction. Namely, this remote is going to fly somewhere into the audience and hopefully not hit anyone. But appreciate what we're doing here. We're making a prediction for an experiment that has not happened yet. A question that I then always like to ask is, well, how do you know that this is going to happen? Well, the obvious answer is, well, we've seen it before. I have 5-year-old twin boys. They're very, very skilled at throwing things at places, and they know exactly what's going to happen. But how do they know that? They've never opened a book on physics. They don't know how to read, but they've seen it before. What we really do is when perceiving our environment is that we're making predictions for experiments, for events that have not happened yet. And these predictions are based on our experience. Now, if we fully appreciate that, then, not thinking again about my little children, what they have a good understanding for are the things that they can touch, which are about the size of their size, that move at speeds that they can perceive, that they can watch, and that are also at energy scales, but that means temperatures that they can understand, room temperature. Wouldn't it be very arrogant to assume that what we perceive around ourselves fully describes reality at very short length scales, at very low temperatures, at very low energies, or at very high energies? So why would we assume that cosmological objects like galaxies behave exactly like a remote that I'm throwing into an audience? Why would we assume that atoms that we can't even see with our own eyes behave like things that we can touch? Well, the truth is, they're not. It's exactly like the example that I showed you before. We only have access to a certain amount of information. And based on the information that we have, we make a prediction for how things should behave. But the universe is a little bit more complicated than that. Here's a famous example. Most of the perception, most of the measurement that we're taking is carried by light. We've already seen examples today when talking, so in particular when, sorry, looks a little bit weird on the screen here, got confused for a second. But this is exactly what I mean, light. Light carries information. The light, this tells me what things should look like, tells me something about my reality. Light, the way that we usually perceive it, is a wave. For instance, we had earlier, when we were talking about music, a work called wave mechanics. We saw examples of remote sensing, which means we're literally taking pictures of the ground from a satellite. And most of the information that is carried, that determines how we make a prediction, is carried by light. This light behaves like a wave. How do we know that it's a wave? Well, you do these double-slit experiments, and later on, When you go outside to the pond, you can do the same experiments. If you throw one rock into the pond, you're going to see ripples. That's a wave. If you throw two rocks, you're going to see an interference pattern. And this basically just means if a maximum of a wave hits another maximum, you get amplification. And if one wave is oscillating up, the other one is going down, you get destructive interference. That's called an interference pattern. But the Nobel Prize was just awarded for photons, which is apparently light particles. So what is that? Where are the particles in this picture here? Well, the issue is you can perform exactly the same experiment with particles that we understand. If you take a bunch of electrons, real particles, little marbles, and shoot them towards a double slit, what you find is exactly the same interference pattern as you would find when performing the experiment with a wave. So how is that possible? Well, it's possible because in this particular experiment, we're taking a measurement on the wave properties of reality. This is often coded in terms of Schrödinger's cat. So I could be talking a lot about Schrödinger and why he came up with that and different interpretations of quantum mechanics, but none of that actually matters. The only thing that matters is the following. When thinking about Schrödinger's cat, it's not true that classically a being is dead and alive at the same time, but rather that depending on the information that we have, we cannot make a deterministic prediction. So keeping that in mind, how does the Gedanken experiment work? So assume you have a closed box. And inside this closed box, you have a cat that was initially alive. Stuffed it in. Cat is not going to be very happy, but you put it in there. Next to the cat, there's a little bucket with poison. Choose your poison, whatever you like. But it should work quick enough that as soon as the bucket is kicked, literally, the cat also kicks the bucket. Now, as long as you haven't opened the box, you don't know whether the cat has kicked the bucket or whether there's some, in the original experiment, there's some complicated nuclear physics example of when the bucket is going to kick over. But the essence really is that as long as you haven't opened the box, you don't know whether the cat has been exposed to the poison. Now, in old traditional interpretation of quantum mechanics, people then often say, yeah, the cat is actually in a quantum superposition of being alive and dead at the same time. What does it actually mean? It means nothing. It means that you cannot make a prediction with certainty. It's not like the remote that I'm throwing somewhere and you know exactly where it's going to hit. You don't know what the state the cat is in because you haven't measured. In quantum logic, this is then usually represented as what you see on the slide here. In classical logic, the cat is dead or alive, 0 or 1, black or white, true or false. If you know a little bit of computer science, you know that there's fuzzy logic, which is somewhere in between, where you can't make a deterministic prediction anymore, but you know that with a certain probability, you're either in 0 or 1. So that's a circle. Quantum reality is actually even more complicated than that, but in this picture it becomes very easy. The classical world, what we perceive at our length scales, that's 0 and 1. It's a zero-dimensional object. It's just a point. Whereas the quantum logic is a two-dimensional sphere. So you go into 3 dimensions. Again, this means nothing else, but there's more information encoded in reality than we can usually perceive. Exactly what I showed you before with the rectangle, circle, and the cylinder. But now we have a question. If there's more information in the universe that we can perceive, how come that we never see it at all? Let me ask another question. If I asked you now, where do you see me? Where am I? You would probably say that I'm somewhere here on stage. If I asked you, you would tell me, well, I'm somewhere here on stage. And if I asked you, you would also tell me that I'm standing somewhere here on stage. How do you actually know that? How do all 3 of you know that I'm really here? Well, you've decided that this is real, that this is objective, because you agree on the outcome of the measurement that you have performed. And all 3 of you have reached consensus. If sufficiently many independent observers agree on the measurement outcome, then this is what we call objective reality. But now we need to think through what's really happening, because neither of the 3 of you are actually interacting with me directly. But what's really happening is that this incredibly bright light up there is shooting photons at me. And of the photons that interact with me, an itsy-bitsy tiny fraction is scattered off towards you, and you intercept these photons. This tiny fraction of the light that is carried from the lamp up there, scattered off me, towards your eyes, you reach the conclusion that I'm standing right here. And multiple independent observers, all of you, agree on the fact that I'm here. This is objective. This is reality. Now, the question that we need to ask, and this is what we do in our work, is trying to understand, where does all the quantum information go? So how much of the environment would you have to intercept to see any quantum properties of my being? Well, what you can show is this: if you were able to intercept literally everything, all the photons here in the room, you would indeed be able to reconstruct my full quantum state. But typically, that's not what's happening. And the only information that survives the scattering of the photons of objects in the universe, that's the classical information. And this is why it's called quantum Darwinism, the survival of the fittest information. The classical information is the one that survives the interaction. Schematically, this is what it looks like. Whenever we talk about classical objects, we have a system sitting somewhere that interacts with a messy, noisy environment, typically photons. Then you have many observers from the outside, and if all the observers on the outside that intercept only a tiny fraction of the environment that the object has interacted with agree on the state, then it's objectively there. All right, as I promised you, it was a bit of a wild ride through theoretical quantum physics. And obviously, I hope I didn't disappoint you too much. I didn't show you a single equation. Of course, this is something that we need to write down in math and do complicated things, which looks a little bit like speaking in tongues, but none of that really matters. What really matters is the following. The quantum universe, the universe, is a lot more complicated than we perceive based on our experiences that we've made as little children. There's a lot of information out there that we do not have access to simply because we didn't evolve at energies or length scales where this information was crucial. Our classical reality, what we perceive to be real, is really based on the fact that different observers that take the same measurement agree on the measurement outcome. And the rest of the quantum information that we don't have access to, that's smeared out. That is suppressed by the noisy environment of everything else. Thank you.